welcome to another edition of NAMSSN tutorial. So this is a MAT 331 complex analysis 1. So in the last video we talked about complex number and then all the operations on complex number. So today we want to discuss about complex variables. So under which we are going to talk about how to express a complex variable in real and imaginary parts. So we'll discuss about differentiability, analytic function, and harmonic function. Now, functions of complex variables. Now, in functions, you remember from complex number, we define complex number as an algebraic expression in form of a plus or minus ib. So where a represents the real part and then ib represents the imaginary part. So suppose I have a function f of z is equals to u xy plus I v xy, where this part, it means u is a function of x and y, and the other part here, v is also a function of x and y. So everything here represents the real part. This is the real part. And because of this I that is here now, makes everything here to be the imaginary part. So any number, any expression in this form is a complex variables, f of z. So u of xy plus I v of xy. So the first thing we need to know is that how do we change expression to u and iv. Let's start, for example, let's express e raised to power z, let's say f of z equals to e raised to power z into real and imaginary parts. So I want to express f of z equals to e raised to power z into real and imaginary parts. So it means that I want to express this e raised to power z into these two functions. So you recall that z from our complex number, z can be expressed as either Cartesian form or rectangular form, x plus iy. Z can also be expressed in polar form, r into cos theta plus I sin theta. So and z can also be expressed as r exponential I theta. This is the exponential form of complex number. So which one are we going to pick? So if I pick the first one by saying f of z equals to e raised to power, this z now, I will change it to e raised to power x plus iy. E raised to power x plus iy. And you know from indices, x raised to power a times x raised to power b. So I can split this one into ex, eiy, ex, eiy. So with that, you know from Euler formula goes like this: e raised to power I theta equals to cos theta plus I sin theta. So here now, I have e raised to power iy. So if I express this e raised to power iy in terms of this e raised to power I theta, so we are going to have e raised to power x into bracket this e raised to power iy now, just like this. It will now be cos y plus I sin y, because e raised to power I theta is cos theta plus I sin theta. So e raised to power iy, here now y represents theta, it will be cos y plus I sin y. So if we remove the bracket, f of z, so f of z will now be e raised to power x cos y plus I e raised to power x sin y. So this e raised to power x plus y, cos y represents the real part, and I is already here now. This e raised to power x sin y represents the imaginary part. So this is the real part and this is the imaginary part of this exponential z. So this is how we express exponential z in complex of into function of complex variable, real and imaginary parts. That's one example. Another example. Suppose I want to express f of z equals to 1 over z bar squared. F of z equals to 1 over z bar squared into real and imaginary parts. So I want to express this function 1 over z bar. So I'll first ask myself, what is z bar? You know, from the beginning of this course, we said that z is equals to x plus iy, rectangular form. So if I have z bar represents the conjugate of this x plus iy to now be x minus iy. So here now I have f of z is equals to 1 over z bar squared. That's 1 over x minus iy all squared. 1 over x minus iy all squared. How will I express this one? So what I'm going to do is that, okay, I open the bracket. So if I open the bracket, I'm going to have 1 over x minus iy, x minus iy. 1 over x minus iy. And then, what are we going to have? We are going to have 1 over, open the bracket, that's x squared minus, okay, opening the bracket, we are going to have x squared minus 2ixy minus iy times minus iy. That's minus y squared. So if I now write it as 1 over x squared minus y squared minus 2ixy. So, well, I'm not yet satisfied with what I have. I'm having 1 over so we are having 1 over so we're having 1 over x squared minus y squared minus 2ixy. So the next thing is that I'll rationalize. If I rationalize this part, so it will be times the conjugate of these two. That's x squared minus y squared plus 2ixy. Remember from solve, if you are rationalizing, you just change the sign that is here. Divided by x squared minus y squared plus 2ixy. Let me bracket this one like this. So 1 times x squared. So this one will be x squared minus y squared. 1 times 2ixy. 2ixy. All over x squared minus y squared times x squared minus y squared. It will give us x squared minus y squared all raised to power 2. X squared minus y squared, x squared minus y squared. So difference of 2 squared. So minus 2ixy times plus 2ixy. So it will give us, well, 2 times 2 is 4. X and y give us x squared, y squared. I times I, that's I squared. And we know that I squared is minus 1. Minus, plus, and that minus to give us plus. So we can just separate into partial fraction now. It will now be x squared minus y squared all over x squared minus y squared all squared plus 4x squared y squared. And with the I that is here now, this one will now be plus I 2xy divided by all this as well. Divided by x squared plus y squared all squared plus 4x squared y squared. Because we are going to need this separation, how to separate into real and imaginary parts. We are going to need them in the long run when we get to analytic function and harmonic function. So everything here now represent the real part. Everything here represent the real part. The one with I here now represents the imaginary part. So that is another example. So let's try more. Suppose I was given to separate this function f of z Oh yeah, sorry. This is x squared minus y squared all squared plus 4. Thank you. Suppose I was given f of z equals to sine z to separate into real and imaginary part, sine z. So it will be f of z equals to, we know that z equals to x plus iy. This will be sine x plus iy. And you remember from elementary that if I have sine a plus b from trig, sine a plus b is equals to sine a plus b plus cos a sine b, right? So let's mark this. So I now want to expand sine x plus iy using this identity. So I'll say f of z equals to sine a, that's sine x, cos b, this is b, cos iy, plus cos a, that's cos x, sine b, sine iy. So what do we now need here? So in the previous video, I discussed something about odd and even function. When we were doing the Movies theorem, if I have something like cos minus theta, to still give us cos theta. But if I have sine minus theta, this minus will come to the back like this. It will be minus sine theta. So because sine behave as an odd function and cos behave as an even function, that's one thing. And another thing is that there is a relationship between trigonometric function and hyperbolic function. There is a relationship between trigonometric function and hyperbolic function. What's that relationship? If I have sine I theta, for example, sine I theta, this one is normal trig, sine I theta. It will now give us, now one thing is that sine is an odd function. This I will go out to be I. With that, this sine will now change to hyperbolic of sine. It now equals to I sine h of theta. Sine I theta, because sine is an odd function, this I will not stay here again to go to the back. And with that transformation, this trig will now change to hyperbolic function. Sine I theta is I sine h of theta. For example, let's say I have sine 2ix, for example, sine 2ix. So this I now, it will move to the back to turn to I. And then this trig, sine, it will now change to sine h of this remaining angle, 2x. That is how sine behaves. And also, if I have cos, let's say I have cos I theta. Cos is an even function. So this I will not have any effect. But with the introduction of I here now, it will now turn to cos theta. So cos I theta will be cos theta. But sine I theta, because sine is an odd function, it will be I sine h theta. So that is how sine and cos behave. So from here now, we are having sine x cos iy plus cos x sine iy. So what do we do? So we just separate that f of z equals to, here now we have cos iy now, cos iy. So this I will change this cos to hyperbolic cos. It will now be sine x, sorry viewers, it will turn to f of z equals to sine x cos iy. This I will now turn to cos y, sine s cos iy. And from here now we have sine iy. This I and sine, sine is an odd function. This I will move to the back like this. It will turn to I, and this part of sine will now turn to hyperbolic sine. So we are going to have I cos s sine hyperbolic y. So with that now, we've gotten what we need. Everything here now represent the real part. Because of I that is here now, everything here represent the imaginary part. So real and imaginary. So that is how we separate a complex variables into real and imaginary parts. Now, the next aspect is analytic function. Analytic function. So when a function is said to be analytic, a function f of z is said to be analytic if that function f of z is not only differentiable at z naught, but also at the neighborhood of z naught. What's the meaning of all this? Now, let's go back to elementary calculus. Suppose I have y equals to x raised to power 2 now, and I was asked to differentiate this function at x equals to 1. It means that I will take the derivative with respect to x, that's 2x. Then if I want to differentiate at x equals to 1, I'll put x equals to 1 here. That's 2 times 1, 2. It means that this particular function is differentiable at x equals to 1. So in the case of complex variables, a complex variable will be analytic if that function is not only differentiable at a particular point z naught. Suppose we have a curve now, and let's say this curve is f of z. This is y axis and this is x axis. And then, okay, I pick an arbitrary point, z naught. Let's just pick any point. Let's say I pick any point here. Let's call it z naught. And then I differentiate this function, f prime of z. I differentiate this function at this z naught, at z naught. It means that when I differentiated it, let's say my f of z is like z squared plus 3z. Let's just assume that this is our f of z. And I differentiate it, f prime of z. That will be 2z plus 3. I now put z naught. Z naught is a particular point along x-axis. Suppose I put z naught now. Okay, I get an answer. So now, if this particular function, suppose I pick another arbitrary point along this z naught at the neighborhood. Let's say I pick a point here now. Let me call this point the interval from this z naught to a point here now. Let me call it dz. And I differentiate this function again at this point, and I get an answer like the function is differentiable. Let's say I pick another arbitrary point downward like this. If I pick another point, let's say I move like this now. Okay, I have a point here. So that point is also neighborhood to this z naught. Let me call that one. Okay, let's say this one is dz1. Let's say this one is dz2. And I differentiate this function f of z at this neighborhood closer to z naught. And also I get a value. It means that this particular function is analytic at this z naught. It means that a function is said to be analytic at a particular point z naught if that function is differentiable at that z naught and is also differentiable at the neighborhood of that z naught. So that is what analytic function is all about. Now, how do we now know that this function is analytic? There is a way of knowing a particular function f of z is analytic. So let's prove it. Now, because f of z equals to what? F of z equals to, from the beginning, f of z equals to u of xy plus iv of xy. So I want to check, there is one formula we normally use to check if a function is analytic. So if f of z equals to u xy plus iv xy. Now you remember differentiation from first principle. How we normally differentiate from first principle? If y is equals to something, you add increment to both sides. Now, I will try to differentiate this equation partially with respect to the variables. So the first thing is that, let me say recall that df dz, for example, if I want to differentiate the function z with respect to z, is equals to f of z plus dz minus f of z divided by dz at limit at which dz tends to 0. This is like first principle. So this idea is what I'm going to use here now to test whether this idea is what I'm going to use to know how we normally check if a function is analytic. Now, I have f of z equals to uxy plus ivxy now. I'll now take the increment of both sides by taking f of z plus dz. F of z plus dz. Okay. it means that this is u of xy. I'll take the increment of these two. This one will also be u of x plus dx, common y plus dy, right? And also I'll take the increment of this one too, plus I v of x plus dx, common y plus dy. After taking the increments, this is like step 1. Then the second step is that I will subtract f of z from both sides. So we are going to have f of z plus dz minus f of z is equals to u of x plus dx, common y plus dy, plus iv of x plus dx, common y plus dy, minus what? Minus f of z. On this right hand side, I'm supposed to subtract minus f of z. But here, what is my f of z? All this. So I'll now say minus everything that is here. That's minus u xy minus iv xy. And after that, the third step, divide both sides by dz. So if I divide both sides by dz, now from here now, I need to say, oh, this one to divide by dz. But you know that z is equals to x plus iy. If z is x plus iy, if I take the partial derivative of both sides, dz, that's dx plus I dy. So instead of using dz here, I'll just say, oh, over dx plus I dy over dx plus I dy divided by dx plus I dy. And then the next thing is to take the limit. Let me put it here. The next thing is to take the limit. Now to take the limit at which dz approaches 0, because z is in rectangular form, y-axis and x-axis. So I'll take the limit one by one. So taking the limit. Now let's first take the limit along real axis. Along real axis. The meaning of along real axis is that we are considering this axis, this y component to be 0. That is, the y will be 0. So if the y is 0 now, from here, anywhere you see the y, just cancel it. So if I'm taking the limit of this one now, this one will be 0, this one will be 0, the one here will be 0, this one will be 0, this one will be 0. So we are going to have, so everything here now, everything here has represent df dz. So we are going to have df dz is equals to, so it will remain u x plus dx. This one is 0 now, comma y. This one is 0 divided by dx, right? And here too, we are taking this one is 0, this one is 0, plus iv x plus dx, comma y divided by dx. This one is 0 minus, minus u of xy minus iv of xy divided by dx. So what do you observe? So what is here is just like partial derivative of u with respect to x. You know, if I have f of xy, for example, is equals to x squared plus 3xy. If they ask us to differentiate f partially with respect to x, it means that we only focus on x variables. So if I differentiate x, that's 2x, differentiate x that is here, that's 3. So what we have here now is just like differentiation of u with respect to x alone, differentiation of v with respect to x alone. So we are going to have the f dz is equals to, what is here now? What is here? It's just like du dx plus v and x I dv dx. What we have here now? We are having df dz is equals to u of x plus ds and u of x divided by ds. So this is like partial derivative of u with respect to x. And what we have here is v of x plus ds and minus v of xy ds. So this one is just like partial derivative of v with respect to x. So that's one. This is when I take the limit along the x-axis, the real axis. So I have one. Then the next thing is that I'll now take the limit again along the imaginary axis. Well, let me clean the diagram that is there. So if we take the limits along the imaginary axis, so taking the limits along imaginary axis. What does that mean? I'm considering y axis alone. So that's the x will be 0. The x will be 0. So from here now, if our dx is 0, this one will be 0. The second one here will be 0. This part is 0. This part is 0. This one is 0. So we are going to have the f dz is equals to u. This one is 0. We are going to have u of x alone. Comma, this one will still be there. Y plus dy divided by, this one is 0. I dy plus iv, this one is 0. Iv of x, comma, y plus dy. This one is 0. Divided by I dy. And then we have minus u of xy minus iv of xy divided by, this one is 0, I dy. So what is here now? The f dz is equals to, this is just like partial derivative of this u with respect to y, because we are taking x as constant, we are differentiating u partially with respect to y. So what we have here is just like du divided by dy. Don't forget I is here. So this is like du divided by I dy. And then what is here now? Well, I will cancel I from here. So we are going to have plus, this is like partial derivative of v with respect to y, dv dy. So this is the first derivative, this is the second derivative. So we now equate two of them. If I equate the f dz that is here and the f dz that is here, so if I equate these two partial derivatives, we are going to arrive at the famous equation known as Cauchy-Riemann equation that we will be using to test whether a function is analytic or not. So if I equate these two, we are going to get du dx plus I dv dx is equals to du divided by I dy plus dv divided by dy. So in that case, what are we going to do? So we are going to have real and imaginary parts. So from here now, this is like real parts. This is also real parts. And we equate the real part. If I equate the real part, we are going to have du dx is equals to dv dy. That's one equation. And if I equate the imaginary part, these two are the imaginary parts. So we are having I dv dx is equals to du divided by I dy. So I did not need I. So what am I going to do to cancel I from both sides? If I multiply both sides by I, I just say this side times I, this side also times I. So I times I here will cancel out. I times I square is minus 1. So this one will now be du dy is equals to I square is minus 1. This one will now be minus dv dx. So these two equations, they are the tools that we'll be using to test whether any function is analytic or not. So let's now conclude. Let's conclude. So in conclusion, In conclusion, in conclusion, a function f of z is said to be analytic, if all these partial derivative hold. If the partial derivative, if the four partial derivatives hold. What are the partial derivatives? Du dx is equals to dv dy, and then du dy is equals to minus dv dx. So this equation is what we call Cauchy-Riemann equation. Cauchy-Riemann equation. So this four partial derivative is what we are going to be using to test whether any function is analytic. Note that the function you want to test, you must have separated them into real and imaginary before you take these four partial derivatives. So let's check for example. So we need this. So I will not clean that side. Now, let's take for example. So let's test for analyticity of f of z equals to 1 over z. So this function, I want to test whether this function is analytic. Now, what do I need? The first thing is that I have to separate this function into real and imaginary as we done earlier on. So if I have f of z to equals to 1 over z, I know that z is equals to x plus iy. Then, for me to separate, I will rationalize this one by multiplying by the conjugate. So 1 times x, 1 times iy is iy, or x times x squared. These two will cancel out. Iy times iy, I know that y times y is y squared. This one will be plus y squared, right? So that's f of z. And then this one will now become, okay, we can cut this fraction into two by having x divided by x squared plus y squared minus iy divided by x squared plus y squared. So it means that, don't forget, our f of z is always in form of u of xy plus iv of xy, where u represents the real part. So what is our u now? Our u from this function is x over x squared plus y squared. And what is v? V is the imaginary part, the part with I. V is minus y over x squared plus y squared. So then, for me to check whether this function is analytic, I will test this function from these four partial derivatives. Then I'll first take the partial derivative of u with respect to x. If I differentiate u with respect to s, how will I differentiate something like this? I'm going to use quotient rule. Why? Because I have x here, I also have x here. So you remember quotient rule from elementary calculus. If I want to differentiate this thing partially, quotient rule is v du minus u dv all over v squared, something like this. where my numerator is u, my denominator is v. V du, it means that I will write this x squared plus y squared. I will differentiate it. Don't forget, I'm differentiating with respect to what? With respect to x. So if I differentiate x is 1 minus u dv, I will write this x. I will differentiate x squared plus y squared partially with respect to x. It means that I'm only differentiating x that is here. That's 2x all over v squared. X squared plus y squared all squared. Open the brackets. So du dx, it will be, this is x squared minus 2x squared, that's minus x squared and y squared. So this one will give us y squared minus x squared all over x squared plus y squared all squared. That's the first partial derivative. Then I'll differentiate the other one too with respect to y. V, this is v now. Again, you first separate that function into real and imaginary before you go by this one. So v is equals to minus y over x squared plus y squared. I will also differentiate that one with respect to y. dv dy, I will use the same rule, quotient rule. I will have over v squared. Let me write that one first. The first one is a v du. This is v. X squared plus y squared. Differentiate this one partially with respect to y. If I differentiate minus y, that has minus 1. Minus is here. Minus u dv. This is u now. U is also negative expression. So it will now be plus y. dv, differentiate this one with respect to y. If I differentiate y squared, that's 2y. Removing the bracket, we are going to have minus x squared plus minus y squared plus 2y squared. So that one will also give us a y squared minus x squared all over x squared plus y squared all squared. So you observe that du dx is equals to dv dy. The first partial derivative hold. Then the second one, I will also differentiate u with respect to x. Okay, I'll differentiate u with respect to y. This same function, I'll differentiate it with respect to y. If I want to differentiate this one with respect to y, I will have x squared plus y squared all squared, right? V is x squared plus y squared. Du, it means that I want to differentiate x with respect to y. That will be 0. Is 0. Minus, right, x, differentiate this one with respect to y, 2y. Anything times 0 is 0. So this one will be minus 2xy. This one is what we are going to have left. Divided by x squared plus y squared all squared. That's du dy. Then what else do I need? dv dx. dv dx. It means that I will differentiate this one now with respect to x. Or if I'm differentiating with respect to x, I'm going to have x squared plus y squared all squared. V is x squared plus y squared. Du, you differentiate what is here with respect to what? Here we are differentiating with respect to x. That one also will be 0. Minus u is negative number, so that's plus y now. D of the second one with respect to y, sorry, with respect to x. So if I differentiate this one, that's 2x. So anything times 0 is 0. So we are going to have 2xy all over x squared plus y squared all squared. So what do you observe? This one and this minus is here. So it has validated this one now. So du dy is minus 2xy. dv dx is 2x over x squared plus y squared. Which means that the four partial derivative hold. The first one is also equals to this. The negative derivative of the second one is equals to this. So it means that this function 1 over z is analytic. So that is how we check if a function is analytic. So under this context of complex variables, so our knowledge of differentiation, we really need to go and revise all those basic rules of differentiation so that it won't be difficult while evaluating it. So let's try one more. Let's test for analyticity of tests for analyticity of f of z equals to log z. Let's do this. So log z. Let's test whether this function is analytic. What's the first thing we are going to do? We will first separate the function into real and imaginary parts. If I have f of z equals to log z, f of z is equals to log z. And we know that z is a complex number. We can express z in rectangular form or in polar form or in exponential form. If I start by exponential form of complex number, we know that this is the exponential form, r exponential I theta. So if I say that, oh, f of z is equals to log r exponential I theta. What is r? From our previous video, r is the modulus of the two complex number, while theta is the what? Theta is the argument. So this one will now be f of z is equals to log r plus log e of I theta. Why do I introduce plus there? You know, from properties of logarithm, if I have log a times b, it will be log a plus log b. So we separate them like that. So f of z will now equals to log r. If z is equals to x plus iy, what is r? R will be square root of x squared plus y squared, right? So this one will now be log square root of x squared plus y squared. And this is log, this is e. Two of them will cancel out. It will now remain I theta. And what is theta? Theta is the argument. So this one will now be log square root of x squared plus y squared plus I tan inverse of y over x. I tan inverse of y over x. So this is our function z. Then the next thing is to do what? To take the four partial derivative. We should differentiate the first one with respect to s and then differentiate the other one too. So what is the... So this is our u, the real part. U is equals to log of square root of x squared plus y squared. And v is the tan inverse of y over x. Tan inverse of y over x. Now differentiate u partially with respect to s. Don't forget in what is it called? Chain rule. Chain rule of differentiation. If I'm differentiating logarithm, if I'm differentiating a log function, log is 1 over. So log of this, it will be 1 over square root of x squared plus y squared. And if I'm differentiating something with roots, it will be 1 over 2 roots of that x squared plus y squared. And if I will now differentiate what is here with respect to s, if I differentiate x squared, that's 2x. So viewers, please just go and revisit your basic differentiation on logarithm and then chain rule and other rules of differentiation. So 2 will cancel 2. Du dx will now be root and root. We are going to have x squared plus y squared times x. And then I will also differentiate the other one with respect to y. I will differentiate tan inverse. Don't forget, if I'm differentiating tan inverse, is 1 over 1 plus square of that thing we are differentiating. 1 over 1 plus y squared over x squared. Multiply by, we will then differentiate this y over s partially with respect to y. If I have y over x, it's just like having y times 1 over x. So if I differentiate y that is here, that's 1. This 1 over x will be constant. So if I differentiate y over s, that's 1 over x. And then you simplify this. If I simplify, I'm going to have x squared divided by x squared plus y squared times 1 over x. So x will remove 1 square. Our answer will be x over x squared plus y squared. You observe that the partial derivative of first one and the partial derivative of the second one, they are equal. It means that the first condition hold. Then you also differentiate u with respect to y. If I differentiate u with respect to y, it means that this log root x squared plus y squared, here now you will differentiate with respect to y. How will I do that? The same way. The derivative of log function is 1 over that function you are differentiating, 1 over x squared plus y squared. The derivative of something inside square root is 1 over square, 1 over 2 roots. That stuff you are differentiating times. You will now differentiate what is here with respect to the variable you are talking about, with respect to y. So if I differentiate y squared with respect to y, that's 2y. And from here, these two can cancel out. We are going to have y divided by root and root. They will go. So y divided by x squared plus y squared. And what else will I do? I will also differentiate the other one, dv now, with respect to x. Before partial derivative, I think it will hold. If I differentiate tan inverse with respect to x now, the derivative of tan inverse is 1 over 1 plus the square. The derivative of tan inverse is 1 over 1 plus the square of this stuff, 1 over 1 plus y squared over x squared times. You will now differentiate this y over s partially now with respect to s. Now this is like y over x. If I differentiate y over s with respect to x, it means that I'm only differentiating 1 over s that is here. And the derivative of 1 over s is minus 1 over x squared. And then with y. So if I differentiate that y over s, I'm going to have minus y divided by x squared. Then you simplify this. We are going to have x squared divided by x squared plus y squared times minus y over x squared. So x squared cancel x squared. So we finally arrive at minus y over x squared plus y squared. And then before partial derivative as old, derivative of the first one is equals to that of the second one. Derivative of the third one is equals to minus derivative of the last one. Therefore, logarithm function is an analytic function. So that is all about analytic function. So the next thing is a harmonic function. Harmonic function. What is an harmonic function? What is an harmonic function? A function f of z is said to be harmonic. Well, it's harmonic if it satisfies the Laplace equation. What is Laplace equation? From our Cauchy-Riemann equation, we know that du dx is equals to dv dy. Say this is equation 1. And then du dy is equals to minus dv dx. Say this is equation 2. If I differentiate equation 1 with respect to x, if I differentiate equation 1 with respect to s, so this one will be d square u dx squared, right? This is already du dx. I want to differentiate again with respect to x. That's d square u dx squared. And if I differentiate this part too with respect to x, it will also be d square v dy then dx. Because I have dv dy, and I also want to differentiate it again with respect to s. That's a second derivative of v partially with respect to y and x. And if I also differentiate, 2 now with respect to y, if I differentiate 2 with respect to y, so I'm going to have d square u dy squared. Differentiate this one with respect to y, that's minus d square v dx and dy, right? So if we now add these two together, if I add these two together now, let's say this is 3 and this is 4. If I add them together, we are going to have d square u dx squared plus d square u dy squared is equals to adding these two. That's d square v dy dx minus d square v dx dy. So dy dx and dx dy are the same thing. So this one will cancel out. That will be 0. Therefore, d square u dx squared plus d square u dy squared equals to 0. So this is the Laplace equation they are talking about. So any complex variables that satisfy this Laplace equation is harmonic. That is, if u is a function of x and y, and then d square u dx squared plus d square u dy squared is equals to 0, it means that the function is what? Harmonic. So then u equals to f of xy is harmonic. So let's check examples. So given that u is equals to 2x into bracket 1 plus y, show that u is harmonic. So we have u is equals to 2x into bracket 1 minus y. That's like the real part of a certain function of complex variable. So we want to check whether this function is harmonic. So if I first open the bracket, this is 2x minus 2xy, u equals to 2x minus 2xy. Then I will take the partial derivative of u with respect to s. So du dx is equals to 2 minus 2y. Then I'll differentiate again. And let me put that one here. D square u dx squared. If I differentiate what is here again with respect to s, so there is no x variables here. So d square u dx squared is 0. And then I also differentiate partially with respect to y. If I differentiate with respect to y here, this part will be 0. If I differentiate y that is here, it will be minus 2x. And then d square u dy squared is equal to what? If I differentiate what is here again with respect to y, so this one doesn't have any y variable, so it's 0. So you observe that if I add d square u dx squared to d square u dy squared, it will give me 0. That's 0 plus 0 is 0. Okay, so let's check another examples. Now, given that example 2, we are to show that u is equals to half log x squared plus y squared is harmonic. Let's show that this function is harmonic. Show that this function is harmonic. So we have u equals to half log x squared plus y squared. What do we need? So differentiate partially with respect to x. So what's the u dx? If I'm differentiating log function, so from our previous explanation on analytic function, so if I'm differentiating log, the derivative of log is 1 over that function x squared plus y squared. Then I will now differentiate what is here partially with respect to x. So if I differentiate x squared, 2x, and don't forget we have half from the beginning. So 2 cancel 2. So the u dx is x divided by x squared plus y squared. And then I'll take the second partial derivative of u with respect to x. So it means that I'm differentiating what is here again partially with respect to x. So if I differentiate this, that's quotient through x squared plus y squared all squared. Write this, differentiate x, that's 1, minus, write x, differentiate what is here partially with respect to s, that's 2x. So if I open the bracket, I'm going to have y squared minus x squared divided by x squared plus y squared all squared. That's v du minus u dv. That's quotient through. Then I also take the partial derivative of u with respect to y. This is u. I will differentiate this one partially with respect to y now. So that will be half times the derivative of log is 1 over x squared plus y squared. Then I will differentiate what is here now with respect to y. That's 2y. 2 cancel 2. That will be y over x squared plus y squared. And then I will take the second partial derivative of u with respect to y. That's the square u dy squared. It means that we are differentiating this one again with respect to y this time around. So it will be, you apply quotient through, we are going to have all over v squared like this, and then write this, differentiate y, that's 1, minus, write y, differentiate this one with respect to y, that's 2y. So if we open the bracket, this is x squared plus y squared minus 2y squared. So this one will be x squared minus y squared all over x squared plus y squared all squared. And then for this u to be harmonic, we add these two together. The square u dx squared plus the square u dy squared. It will give us what? These two fractions, we add them together. That's y squared minus x squared divided by x squared plus y squared all squared plus the other one, x squared minus y squared divided by x squared plus y squared all squared. So we have a common denominator. So we are going to have x squared plus y squared all squared. This in this 1. 1 times y squared minus x squared. And this, that's a plus x squared minus y squared. So x squared, remove x squared, y squared cancel y squared. So everything is now 0. It means that the sum of the two partial derivatives give us 0, which means that this function is harmonic. So that will be the end of session. For criticism and correction, you can drop it under the comment.